Welcome, everyone. I'm Vito Ilacqua. I'm a scientist in the Indoor Environment Division of the Office of Radiation and Indoor Air at EPA. Our team has been providing guidance over the past, 15 months now or so to the general public and special stakeholders such as schools and others about how to protect ourselves in indoor environment during this pandemic. And part of that guidance including the use of air cleaners. So we're very pleased today to have distinguished guest speakers that will help make sense of the technology used in these devices. Dr. Elliott Gall is an associate professor at Portland State University in the Department of Mechanical and Materials Engineering. And there he leads the Healthy Buildings Research Laboratory. I bring up the name specifically because that really tells you something about his research that looks at indoor air quality from multiple perspectives simultaneously, from the exposure and health side to energy use and building materials and so on, and as well as the topic of today's webinar, the technologies used to improve indoor air quality. And some of you may also recognize his name from the news, his research has been featured a few times during these days. And Dr. Gall will be alternating in the presentation with Dr. Brent Stephens, who chairs the Department of Civil Architectural and Environmental Engineering at Illinois Institute of Technology. And Dr. Stephens is a star researcher in the world of indoor air quality, and his work also focuses on very similar topics in some ways on energy and air quality in the built environment. I have had the pleasure of working personally with Brent in different roles while at EPA, and in particular, I want to highlight that he was one of the main authors of the EPA Guide to Air Cleaners in the Home, which is available on our website. You can see an image here, and can probably be useful for someone in our audience as a reference for today's topic as well. So after their presentation, we will have some time for questions. Feel free to enter them in the question and answer box throughout the presentation. Given the size of the audience that we expect, we'll have to go through them and combine them to try address those that are of wider interest first. I'll ask that out of consideration for our speakers, we will try not to put them on the spot and ask policy-related questions that are outside of their expertise. And we also ask our speakers to refrain from naming specific brands or products in their answers. So that is the type of question that I will not be able to answer. Two more items before I give the platform to our speakers. First, I really want to emphasize that the views expressed in the presentations are those of the speakers themselves and do not necessarily reflect those of the EPA. And next slide. The second point is this webinar is being recorded, and it will be available as a video, typically a couple of weeks or so after the event. And you can also get to it by searching indoor air quality on the EPA website and following the links to our webinar series. Once the slide comes up, you may also see in there some more examples of webinars that we have posted and that may be of interest to today's participants. I think that's all I wanted to say. Again, we're very pleased to have Brent and Elliott here. Please take it away.
Great, thank you for that introduction. Let Elliott load up here. So Elliott's going to drive the slides today. And it looks like we're clear to go. All right. Great. Well, thanks a lot. So I'm Brent Stephens, and I'll begin presenting. And like Vito said, we'll kind of exchange off here and there. But I just want to thank Vito and Laura and EPA for the invitation and the opportunity to speak today. You know, our goal here is really to try to help shed some light on air cleaning and help navigate sort of the landscape of air cleaning technologies that are currently available for decreasing COVID-19 transmission indoors. Next slide, please. So before we get started, I just want to frame with a little bit of background on kind of where we're coming from and how we think about this. But you know, COVID-19 has in many ways transformed, you know, how we think about infectious disease transmission, especially given that there's increasing recognition of the importance of small particle, or what's conventionally referred to as aerosol particle or aerosol transmission. In the transmission of COVID-19. Especially as evidence continues to mount that aerosol or small particle inhalation is likely a dominant mode of transmission, especially in poorly ventilated indoor environments, right? So we've gone from kind of washing our groceries, you know, over a year ago because of a concern of contaminated surfaces to much more concern around aerosol inhalation. And it's, you know, what we've also sort of understood is that aerosol transmission doesn't necessarily just mean long range transmission. It just largely means, at least from the perspective of an indoor air scientist or like ourselves, that small aerosol particle exposure is important both at short range distances where we know a lot of transmission occurs, but then also at longer range distances, as has been demonstrated in a number of relatively high profile and increasing number of case studies. Next slide. All right. And, you know, I think it's important also to kind of reference how our understanding of transmission mechanisms of COVID-19 has really evolved in the last 15 months or so, as it really has roots in a pretty strong understanding of respiratory emissions of particles from people, which we've understood for quite a while now. And especially important there is that we know that the vast majority of particles emitted during human respiratory activities, things like talking, you know, coughing, sneezing, and even breathing, are quite small particles. So the vast majority by number are smaller than 50 or 100 micrometers, which means that they're capable of remaining suspended in air for long periods of time, and therefore, you know, leading to aerosol inhalation exposure being important. Next slide. And in framing our thinking, of course, it's also important to note that although the SARS-CoV-2 virus, you know, the virus that causes COVID-19, is only around 100 nanometers or 0.1 micrometers, as shown here in diameter, as it exists in the environment enveloped in respiratory fluid, such that it can persist, you know, theoretically in particles ranging from as small as a couple hundred nanometers, 0.2 micrometers or so, to as large as, you know, big 100 micrometer droplets. So there's roughly sort of a, you know, maybe a 3 order of magnitude span or so in size that the SARS-CoV-2 virus can exist in particles in the indoor environment. And the likely importance of small particle or aerosol transmission of SARS-CoV-2 really started to become clearer in the spring of 2020, when some early studies came out showing that SARS-CoV-2 RNA or genetic material, you know, was detected in air samples in hospital environments. For example, showing here is finding finding SARS-CoV-2 virus in particles as small as 0.1 micrometers, and then across the spectrum between about 0.1 and 10 micrometers, all of which are considered sort of airborne suspended particles. And then by the summer, towards the bottom of the slide, by the summer of last year, this became even clearer as the first study that detected viable SARS-CoV-2 virus in aerosol particle samples in a hospital in the US was published, which is shown here, you know, reported in the New York Times as sort of a smoking gun pointing towards the importance of a small particle or aerosol transmission. Next slide. So with that background and this kind of, you know, this increasing understanding of the importance of aerosol transmission, and also the potential for transmission by larger particles and potentially contaminated surfaces in some environments, you know, by the fall of last year, sort of going chronologically here, you know, it was pretty clear to most that the appropriate approach to controlling COVID-19 transmission is this layered approach that relies on multiple strategies to effectively decrease the spread. And so this is probably best visualized in this sort of now famous Swiss cheese model of respiratory virus defense, where each slice represents a type of a control layer. So, for example, on the left there, physical distancing, wearing masks, washing hands. Each one of those has potential to mitigate transmission in different ways. But the problem is each slice is not 100% effective. So, each slice has holes in the defense layer. So if you stack enough of these, though, on top of each other, then the next layer theoretically has the potential to catch, what the previous layer missed. And so if you look to the right, vaccines, which have been developed in historically rapid fashion, are down on this last layer here. What we're really, largely here to talk to you about today is layered toward the middle there, highlighted in red. This sort of ventilation, being outside, and especially this air filtration layer. So this is becoming a really important layer in the defense against COVID-19 transmission, especially as we've understood this importance of small aerosol particles, which again can occur in, transmission can occur in close proximity to other people. And then also has this demonstrated potential for aerosol particles to remain suspended and transport further than these sort of traditionally defined thresholds of 2 meters or 6 feet in close proximity. So as we begin to sort of navigate this landscape of air filtration or air cleaning, I'll just mention some of my own sort of chronological experiences as they date back to the summer of last year, when I started getting contacted by a lot of local businesses and restaurants and schools, both managers, teachers, and students alike, the parents of students, that were exploring ways to improve ventilation, add air cleaning, especially in their buildings. And there's these stories in the Tribune here of local restaurant and business owners, trying everything under the sun, from HEPA air purifiers to better HVAC filters to UV systems to reactive additive air cleaners to extreme heat units to inactivate virus, and so on and so forth. All of this was really this tough landscape to navigate, but people are trying to demonstrate to customers and workers and their occupants that they've taken steps to make their places of business safer and so forth. And then throughout the summer and fall, as we see here, we started seeing more stories, ranging from sort of technical news outlets to the New York Times on how to keep coronavirus at bay, the HVAC filters help or hurt, and so on and so forth. And then fast forward to this spring, just in the last month or two, and maybe you've read a host of other articles documenting struggles, that schools and other building managers and owners have gone through in terms of being, pretty heavily marketed a variety of air cleaning products, trying to decipher whether they work or not, investing in them in many cases, and in some cases deciding to, take them down as concerns of efficacy or safety are raised, by their constituents or what have you. And so the point is, it's essentially a murky landscape that's been on a lot of people's mind without a whole lot of standardization, which leaves some of this interpretation quite challenging. And we're here to try to help navigate this landscape. So navigating this landscape of sort of available air cleaning technologies and air cleaning devices and so forth is also challenging, because you get bombarded in a lot of different ways with statements from manufacturers and sales reps and so on. So perhaps you've seen language like this before, right? So air cleaner technology A uses reactive molecules to destroy pathogens, or air cleaning technology B is the only one that captures the smallest viruses down to 100 nanometers, or air cleaner C delivers 50% more clean air than HEPA filters. Air cleaner D has been successfully installed in 1,000 buildings and has been shown to reduce particles by 20%. And then surely you've seen kind of these classic approaches of air cleaner technology D reduces viable SARS-CoV-2 by over 99% in 60 minutes. Well, that sounds great. What does that really mean? Or even maybe more detailed, right? Independent testing of air cleaner technology E in a 15 cubic foot chamber demonstrates a net 4 log reduction of some pathogen surrogate, for example, after 45 minutes. So we're here to kind of help illuminate what some of this stuff means. So with this background information in mind, we've put together this webinar with the following kind of more detailed goals in mind. We want to understand the prevailing guidance on air cleaning, so we'll go over that relatively briefly. We want to understand air cleaning mechanisms of action and their potential magnitude of impacts on COVID-19 transmission in indoor environments. We want to get a better understanding of air cleaner test standards, approaches, and their limitations. We ultimately want to learn to critically review and interpret air cleaner test reports that are currently available and widely used. And as part of that, we're going to learn to use tools to evaluate air cleaning technologies. And of course, we'll be available to answer common questions that you might have on air cleaning technologies.
Okay, thank you, Brent. This is Elliott Gall, and I'm going to take over. Brent and I will be sort of passing back and forth throughout this talk. We'll take a minute here and review the prevailing guidance on air cleaning for COVID from several organizations, governmental and trade organizations, taking a quick look at their most up-to-date recommendations. As Brent mentioned, we've learned a lot about respiratory viruses in general in the past year, including SARS-CoV-2. We see that reflected in the guidance from various organizations, including the Centers for Disease Control, which we'll start with. As Brent mentioned, the focus of this talk is on interventions like air cleaning, and so we'll look at the CDC's guidance as it relates to air cleaning specifically. Much of that guidance appears in a document posted on their website called Ventilation in Buildings. We see in the CDC's guidance similar language to what Brent mentioned, recommending a layered approach to reducing exposures to SARS-CoV-2. That includes multiple mitigation strategies, the same idea of having layers that can each have some level of efficacy that in combination increase the likelihood of protection. So the CDC recommends ventilation improvements, things like physical distancing, face masking, hand hygiene, and vaccination, similar concepts to what we saw in the Swiss cheese model Brent presented. The CDC recently updated this document to include a benchmark for ventilation as measured by carbon dioxide. CO2 measurements are a long-standing metric that have been used in the building sciences to get a quick assessment of the ventilation of a building. The CDC now recommends that a potential benchmark for a good ventilation in a building is around 800 ppm CO2. If we're looking specifically at air cleaning, these appear in what the CDC calls the mitigation toolbox. They make recommendations to improve central air filtration to as high as possible. We'll see this idea appear throughout this talk that our goal is to provide as much intervention as we can to reduce concentrations of SARS-CoV-2 in the air to reduce risk. They reference an ASHRAE document that we'll look at in a moment. The CDC also suggests the use of portable high-efficiency particulate air or HEPA fan filtration systems, as well as UVGI, ultraviolet germicidal irradiation systems, specifically mentioning UVGI if ventilation and filtration are limited. There's also cautionary language in the CDC's guidance at the moment concerning electronic air cleaners like ionizers, dry hydrogen peroxide, and other chemical fogging systems. We'll talk a little bit more about those in this talk. As I mentioned, the CDC's guidance did reference ASHRAE. ASHRAE has assembled what they're calling an epidemic task force to collect information that exists across ASHRAE, as well as develop new guidance specific for buildings and transmission of COVID-19. The guidance looks overall not inconsistent with what the CDC is recommending. Essentially a layered mitigation approach, including following public health guidance, again, things like hand hygiene, masks, addressing occupancy. Ventilation, filtration, and air cleaning are specifically called out as well. ASHRAE recommends maintaining minimum outdoor air flow rates and using MERV 13 or better filters if possible. Air cleaners are recommended, but only those for which evidence of effectiveness and safety is clear. And again, that's one of our goals of this webinar, is to help you in your assessments of understanding the effectiveness of various air cleaners. ASHRAE also recommends improving or promoting mixing in the space, at least when directional airflows are not required. Steps 4 and 5 relate to maintaining operation of the HVAC system, things like ensuring temperature and humidity set points are maintained. These have an important impact on virus survival rates and particles, and ensuring that's maintained through system commissioning. Lastly, we'll look at the EPA's guidance. So the EPA has promulgated guidance specific to homes and coronavirus. Again, following a layered intervention strategy similar to the Swiss cheese model that Brent showed a visual of. We see similar ideas: increased ventilation with outside air, perhaps by improving natural ventilation, opening doors and windows, Jumping ahead to number 5 there, another opportunity for increasing ventilation suggested by the EPA is to use evaporative coolers or whole house fans. Points 3 and 4 are to use your HVAC system and consider upgrading filters in close alignment with what ASHRAE is suggesting. EPA states that air cleaning by itself is not enough to protect yourself and your family, and offers some ideas for improving the effectiveness of an intervention like an HVAC system filter by running the system continuously, for example, or placing a portable air cleaner in the space if you have one and are looking for additional air cleaning. The overall idea here being that we're looking to implement a layered intervention strategy, and prevailing guidance from authoritative organizations include air cleaning as part of that layered intervention strategy.
All right, so continuing down this line of thinking, Elliott just used a number of terms that may or may not be familiar to you, and also over the last year or so, I think our own thinking around air cleaning technologies has evolved quite a bit. So let's first take a little time to introduce some overarching definitions on air cleaning types, mechanisms, and terminology to kind of help frame how we think. First, I do want to mention and reiterate the disclaimer that Vito had mentioned, that any specific name or make or model or image of a specific product that's shown in these slides, does not imply our endorsement. They're just shown for illustrative purposes, and we've tried to minimize the amount, but there's a little in there. But second, and most importantly, we can kind of think of broadly about the main categories of air cleaning devices and technologies that are available based first on how they're installed. So simply put, you can install air cleaning devices obviously in sort of portable or standalone, fashion. And then there's also a host of in-duct air cleaners. So in the top here, standalone or portable devices. By that, I'm most commonly referring, to standalone devices like those shown on the left from the EPA Guide to Air Cleaners and Filters in the Home. Typically, a fan and filter type combination, but can include other technologies. These have been explored for their impacts on particle concentrations using models and measurements, especially in the last year. But of course, research in this area goes back a long time. You could even be talking about one of these simple box fan filters, shown as the third filter, or as the third image here. And then by standalone, I'm also kind of thinking of things that just essentially aren't integrated into duct systems or existing duct systems. So a lot of upper room ultraviolet germicidal irradiation, UVGI type of approaches shown on the very far right are essentially a standalone system that aren't integrated into HVAC systems. And then in-duct air cleaners are just the opposite. They're in-duct devices that are integrated into an existing HVAC systems, regardless of the type of technology that it might use. Next slide. And so now, speaking of air cleaning technologies, we can also think broadly about the main categories of air cleaning technologies based on how they operate or what mechanism they use to achieve their air cleaning goals. And we can lump these essentially into two main categories. One would be a subtractive type of mechanism, a subtractive air cleaning technology, and another being an additive type of technology. The mechanism of action for a subtractive technology is generally going to be removing or inactivating targeted contaminants from indoor air when they come in contact with the technology. So common examples are, HVAC filters or portable air cleaner filters, so media filters, electrostatic precipitators. For gases, there's sorbent media that capture gases that pass through them and so forth. And some of the key parameters that impact the efficacy or the performance of subtractive technologies are things like the airflow rate. So how much air are you moving through the technology? The airflow rate relative to the volumes. How much air are you moving through the technology relative to the size of the space? Also integral are what we call the single pass efficiency, which is just the removal efficiency of the technology, essentially the difference in the downstream and upstream concentrations right across whatever the technology is. And then you also have to be aware of the potential for any byproduct formation. For example, ozone has been shown to be emitted from a number of electrostatic precipitator type of technologies. So you just have to be aware of that. Now, on the flip side, additive technologies, the mechanism of action here is really you're adding constituents to the air to do whatever the stated purpose is, whether that's remove particles, inactivate microorganisms, or to react with chemical contaminants. So there's a wide variety here that sort of continues to evolve and emerge. Ionizers, ozone generators, plasma generators, sometimes referenced, reactive oxygen species type generators, like and hydrogen peroxide generators, and so forth. These largely all can be grouped in the same category at a high level because they rely on adding, essentially reactive constituents to the air. So some key parameters here that you need to understand, both in terms of how it'll perform in the field and then also how it performed in a test chamber, if that's how it was tested, is what is the type of additive, what's the concentration of additive that results, and then ultimately what's the dose of additive that, say, a microorganism under testing was essentially dosed with. Of course, you want to know what are the additives, like what's the type of additive, and is there any concern for toxicity or anything like that? And then what's also useful to know, and one would want to know, is like what's the potential for byproduct formation. So does this technology form particles or gases that we should be aware of, and what kind of evidence is out there demonstrating one way or the other. Next slide, please. Actually, that bullet is important. So one very important bullet here is that it's important to note that many air cleaners use a combination of technologies. So sometimes you can't just lump them into these convenient categories. You may have an additive technology that's combined with a subtractive technology to get rid of the thing that it added, or a byproduct that it inadvertently added, or what have you. So it's a complex kind of deal here, where not only the types of technologies used is important, but even the configuration is important. And so in thinking about how to evaluate air cleaning technologies, it's of course important to be aware of the relevant standards and metrics that exist. And so, for example, fibrous media filters are probably the most well-characterized type of technology out there. Targeted pollutant is for particles, microbial or otherwise, but mostly characterized for just general particle removal. Filters are rated by ASHRAE Standard 522 here in the US. There's international standard organizations standards for particle removal as well. There's a special HEPA standard for really high efficiency filtration. There's proprietary standards. Maybe you've seen the FPR or MPR types of logos, on filters at the supermarket or the hardware store. And those are filters alone. You need to know how they work in context with the system as well. And then there's also a test standard that's widely used for portable air cleaners. It's not used by every manufacturer, but they're used. And that's the AHAM AC1 clean air delivery rate type of standard. And so look for these kinds of things, because at least you know that there's some standardized way of testing and rating these sorts of products. Electrostatic precipitators, I mentioned, have been shown to emit ozone in a number of studies. These target particles. They're often quite effective at removing particles, although there's no specific rating for them that I'm aware of. Although there is an ozone emissions standard, UL 2998 is the most conservative standard. So you'll look for that sort of thing. There's not as much standardization that I'm aware of in kind of the additive, ionizing, plasma, oxidant generating type of air cleaners. And then there are standards for UVGI, including a couple of ASHRAE standards for targeting microbial particles, both in air and on surfaces. But really, and a very important point to make here is that currently the landscape is challenging to navigate, in part because many technologies and many devices are tested, but they're tested in non-standardized ways, so they can be hard to interpret. So one of our goals today is to illuminate what we can learn, from these types of even non-standardized test reports, so that you can make informed decisions when you're considering, various air cleaning technologies. And so before I hand it back over to Elliott, I just kind of want to get on a soapbox for just a moment and propose at the top here, what I see is what I would really like to see for any type of technology that's being considered for use in buildings for air cleaning. And that is this kind of ideal matrix for demonstrated performance metrics. And so if you imagine across this sort of matrix of efficacy in the first column and byproduct formation on the second column, knowing what we know about a number of air cleaning technologies, they can target particles, they can target chemicals, they can target microbiological particles. Some try to do all of these, Some technologies only do 2 of 3, some technologies only do 1 of 3. But what I'd like to see is for an ideal sort of performance, metric matrix is that every technology at some level has an effectiveness demonstrated for particle, chemical, and or microbiological um, constituents. And then in the right-hand column, that yes, it's been tested for byproduct formation, particles and chemicals. Microbes don't really make sense in that space, but you'd love to see that, and you get a green light on all cells, and then you can consider the technology and move forward. But unfortunately, what is more commonly seen is the matrix below for a particular technology. Here's just an example. It's very common to see, well, we don't. It claims to remove chemicals, but we haven't really seen clear data on effectiveness for that. Or, it claims to remove particles and activate microbes, and yeah, there is some efficacy data. But in my asterisk there, it's a bit difficult to interpret. They told us it was 99% removal after 45 minutes in a chamber. I'm not quite sure. That sounds good. I don't know how to interpret it. Elliott's going to help us walk through that later. And then in the right column, there's often, no information on byproduct formation. Does it form particles or chemicals when it's operating in realistic environments? And so unfortunately, we're left with kind of a patchwork of standard and non-standard test results on some, but not all of these performance metrics. So hopefully we can help motivate a move towards the top rather than the bottom as this sort of field and industry evolves. So with that, I'm going to turn it back over to Elliott now to help kind of frame our quantitative thinking on air cleaners.
All right, great, thanks. So Brent laid out an ideal evaluation matrix for how we might want to consider effectiveness and byproduct formation. In the next set of slides, I'm going to spend some time digging into the fundamentals as to how we might evaluate those various metrics in terms of effectiveness or byproduct formation. And the central tool that we need to be able to do this is what's called a mass balance. A mass balance is simply a model that allows us to predict the impact of an intervention on an indoor contaminant concentration. Whatever that contaminant might be, it could be particle phase, gas phase, or microbiological, like Brent mentioned. In words, a mass balance is quite simple. It's a statement of conservation of mass. You think of it as the accumulation or the quantity of some constituent you care about at some point in time can be expressed if you understand the inputs and outputs to a system. This is not a dissimilar concept to what's happening in your checking account, for example. We apply that concept to an indoor environment where we're tracking the sources or the generation of some constituent and the processes that contribute to its removal or the losses. And we do that through time so that we can understand what we think the concentration of that constituent we care about will be. So I'm showing a schematic here of a simple scenario relevant to SARS-CoV-2 where we have a person emitting infectious viral particles in air. But again, we can express this idea generically for any constituent we care about in the space. This is an equation that expresses conservation of mass in our schematic. The time rate of change of the concentration of something we care about is written on the left-hand side of this equation. We can understand how that's changing through time. Again, if we understand the sources, denoted by the S variable in this equation, and the losses, denoted by the L variable in this equation. So this is what's called the differential equation. I want to assure you that we'll go a little bit into the fundamentals in these next few slides, but one of the goals of this webinar and one of Brent and my goals are to provide some graphical and spreadsheet tools that help you interpret these kinds of ideas without having to go through the math yourself, if that's not something you're comfortable doing. We can solve an equation like this in a couple of ways. We can solve for a slightly more complex solution called a time variant solution that allows us to predict how the concentration of some constituent we care about is changing through time. If the assumptions of our model hold true for an extended period of time, we can solve for a simpler version of an equation called a steady state solution, where the concentration of the pollutant we care about is no longer changing in time. Let's look at this in a little more detail specific to SARS-CoV-2. I'm showing a slightly more complicated schematic where we're expressing the important sources and loss mechanisms of SARS-CoV-2 in an indoor environment. So you see the schematic there includes some additional mechanisms that are important if we want to be able to predict the amount of infectious viral particles that are present in air. That's really the goal here, is we want to drive down the concentration of infectious viral particles to reduce the likelihood of airborne transmission of SARS-CoV-2. So I'm expressing here in this equation, this mass balance equation shown here, the important sources of infectious viral particles, so expressed by G, which is the generation rate of infectious viral particles from an infected person. So there's one important source of infectious viral particles. We typically, but not always, assume that in the outdoor environment, we're not bringing in infectious viral particles to the indoor environment. There are 4 important loss mechanisms we should be thinking about in terms of trying to characterize what's happening in our indoor spaces and to reduce the concentration of infectious viral particles. The first loss mechanism is characterized by this lambda term. This is simply outdoor air ventilation. Flushing air through the space reduces the concentration of infectious viral particles in air. The second parameter, this K-dep, refers to the removal of infectious viral particles through a process called deposition. So, for example, larger particles are subject to gravitational forces more strongly than smaller particles, and they fall out of air more rapidly. That's a contributor to this process that we call deposition. Infectious viral particles can be inactivated as they remain suspended in air, and we want to characterize that inactivation rate because, again, what we care about are infectious virus particles in air. Okay, so these 3 terms are likely present in any given indoor environment. This final term is really the focus of our talk. This mechanism refers to the additional loss of infectious viral particles due to the presence of an air cleaner. And typically, we characterize that with a term that looks like this. The clean air delivery rate, which Brent mentioned, comes out of a test standard like ANSI-AHAM AC1, but we can think of the clean air delivery rate generically. It can apply to any pollutant that we care about, because in thinking about the clean air delivery rate, it's simply the volumetric flow rate of cleaned air, in this case, air free of infectious viral particles due to the air cleaner. And so notice how we introduce this into the equation. It has to be normalized by the volume of the space that we're installing the air cleaner in. We'll talk quite a bit more about that later in this presentation, but that's quite important in understanding how effective an air cleaner will be when you install it in a space. Our ultimate goal is to employ mass balance concepts to understand and predict the level of effectiveness we might realize from a particular intervention. Effectiveness is a formally defined term that we can calculate if we compare the indoor concentrations, in this case of infectious viral particles, with and without an air cleaner operating. So we define the effectiveness with this little variable called sigma. It's simply 1 minus the concentration of infectious viral particles with a control device present, like an air cleaner shown here on the right, divided by the concentration that would be present if the air cleaner was not present. Okay, so effectiveness is a formally defined mathematical term that we can use to understand if our intervention is going to reduce our exposure to infectious viral particles. Let's look at an example. If we take the mass balance equation that we wrote that again characterizes the important loss mechanisms that can be present in an indoor environment, the solution looks like this. The important part is we've introduced this variable called L that's shown in bold. And the math works out such that our 4 contributors to the removal of infectious viral particles, they sum together. This is the mathematical underpinning of how a layering intervention work. So what we see is that the loss due to ventilation or flushing of outdoor air adds with the loss due to inactivation of the virus in aerosol, adds to the deposition, adds to the air cleaning process. So what's really important to understand is what is the summation of all of these removal processes in your space. The high level takeaway is you want this to be as high as possible. So let's look at an example. If we run a model to predict the concentration of infectious viral particles in a 75 cubic meter space and make some assumptions, take no viral particles to be present initially and no viral particles to be present outdoors, we're making a very simple assumption that someone emits 1 micrometer particles that contain infectious materials at a certain rate. Let's look at two scenarios, one where the sum of these four loss mechanisms total 1 per hour, and a second where we've added some intervention. It could be any of these four mechanisms that are enhanced, but they sum to 6 per hour instead. So looking over here at the plot, we see what happens as we enhance the loss mechanisms in the space. The blue line shows the accumulation of infectious viral particles when the loss rate is only 1 per hour. The orange line shows it when it's enhanced to 6 per hour. Okay, we see much greater accumulation with lower loss rates. From this prediction, we can calculate the effectiveness of this intervention. We do this at 1 hour here, for example, and we see that the concentration of our infectious viral particles decreases from 275 number per cubic meter to around 75, which yields an intervention effectiveness of 75%. Okay, so that allows us to calculate formally what that effectiveness is. Again, the high level takeaway though is that we want high values of total loss, which lead to lower indoor particle concentrations, which gives us a high intervention effectiveness. That means our exposures will be reduced in this space. Let's look at some examples of what might be realized in an actual indoor environment. So let's take a look at typical values of L with two types of interventions for a residential space. What I'm showing here in the plot is simply a stacked plot of the loss mechanisms that are typical of this scenario. In this example, imagine in your home, you've attempted to increase the total losses in your space by opening windows and doors to increase outdoor air ventilation. This is a way that you can substantially enhance the flushing or the ventilation of the space. Downsides of this approach are it's highly variable and not easily to predict, but studies in the literature show that you can realize on the order of 5 per hour of outdoor air ventilation with that method. We put in some typical values for the loss rates of virus inactivation and particle deposition. And in this example, we see there's no recirculation air cleaning installed. So we see that, harkening back to the example that I showed in the previous slide, this intervention results in a loss rate on the order of the intervention that we just modeled that showed a 75% intervention effectiveness. If you see in guidance documents a parameter called EACH, the equivalent air changes per hour, what that typically refers to is the summation of the outdoor air exchange rate. In this case, it's 5 per hour, and the equivalent loss rate due to the introduction of air cleaning. In this case, that's not done, so that's 0 per hour. So for this example, the EACH would be 5 per hour. Okay, let's look at a second example. Imagine the same space where instead of enhancing outdoor air ventilation, we increase the loss rate due to the introduction of air cleaning. So this slide is set up exactly the same way, but now we have a baseline level of outdoor air ventilation that's typical of US residences, same values for viral inactivation and particle deposition, but we've instead added 5 per hour of recirculation air cleaning. Okay, so the takeaway from both of these examples is that we have a variety of mechanisms that are contributing to the loss of viral particles. Our goal is to increase that total loss rate to as high as possible. And two opportunities for intervening to do that are really to increase outdoor air ventilation and to introduce air cleaning that can substantially enhance that loss rate. In the next set of slides, we'll look at how these enhanced loss rates relate to risk reduction.
All right, so yeah, continuing on, let's take a quick look at sort of some recommendations for risk reduction targets and tools that are out there to help sort of frame how you think about how much air cleaning or how much loss rate intervention you're going to need. So we can start actually first from the sort of epidemiology literature. You may have seen this recent study just a few weeks ago from the CDC showing that improved ventilation and filtration and also wearing masks in this sort of observational study of 123 elementary schools in Georgia throughout the kind of late fall and early winter of 2020 impacted the incidence of COVID-19. And so I just have a graphical representation of this work. This is a pretty qualitative approach to ventilation and air cleaning, but it's really useful because it's the first that I'm aware that showed this kind of impact. And so the left bar is just the reference, the schools that basically responded to a survey that they didn't do any ventilation improvements. The second bar showed quite a large risk reduction, about a 40% risk reduction for those schools that reported doing something to improve ventilation. That is opening doors, opening windows, or using fans. So kind of qualitative, high level, but risk reductions, shown from that. And then there's another group, the third group here, that showed that responded that they used air filtration only interventions. This typically meant using HEPA filters with or without UVGI, but no extra ventilation. They too showed a risk reduction. And then interestingly, when you combine ventilation and air cleaning, so when schools reported doing both, in the very far right bar, they had about a 50% lower incidence of COVID-19 relative to the baseline scenario. So this is kind of some of the first epidemiological and observational evidence of the impact that ventilation and air cleaning can have, but it's rooted in this mechanistic sort of loss rate enhancement that Elliott just described. And so, moving forward, when you're thinking about your own spaces, next slide, there are more quantitative approaches to sort of suggested loss rates. For example, Joe Allen at Harvard and his Healthy Buildings group for well over a year, I think, has been pretty consistently recommending that spaces target 4 to 6 air changes per hour to minimize COVID-19 transmission. Or you could go down to the bottom there if you want to design like a hospital. ASHRAE Standard 170 sets forth a minimum amount of total air changes per hour of 6 per hour. That includes a minimum of 2 air changes per hour from outdoor air, meaning ventilation, plus a minimum of essentially 4 air changes per hour through supply air, recirculating supply air with MERV 14 filter. So you can combine these and get quantitative sort of targets, and you'll typically see around 4 to 6 air changes per hour as a common recommendation that can be achieved through a combination of ventilation and or air cleaning. Moving forward to the next slide, there's also a couple of relatively well understood approaches to predicting the quantitative risk of COVID-19 transmission in indoor environments. Most of these commonly use this Wells-Riley equation, sort of a mathematical model for infectious disease risk. There's a lot of caveats here, but the main idea is that using an approach like this, I just showed 2 examples here. One can approximate the absolute risk of infection under different sets of assumptions, or a bit more accurately, the relative risk between 2 scenarios. So in both cases here, the figure on the left is adapted from a choir practice investigation, where essentially you could envision if your baseline total loss rate, combined between ventilation, deposition, filtration, and activation is only say 2 per hour, you'd have an estimated 70% probability of infection in this space. And if you're able to boost that to say 6 air changes or 8 air changes equivalent per hour, multiplying by 3 or 4x, you're able to sort of halve the infection risk in that scenario. And on the right, it's just another example from the recent literature showing the impact of increasing equivalent air changes. So if you want targeted quantitative targets for how much ventilation and or air cleaning you need, there are tools available to you. And they're based largely on those sorts of approaches. We've used some of those approaches in our own work as well. So while ventilation and air cleaning can both be additive, they can also be compared to one another to make decisions on the basis of not only predicted risk reduction, but also on total cost of operation. And so the long and short, if you're going to ventilate, you got to bring in more outdoor air. And in climates like Chicago and Phoenix, if you don't have heat or energy recovery, that can cost quite a bit of money to achieve a targeted risk reduction. And so actually dating back to a paper of ours from 2013, we use these Wells-Riley approach to estimate the impacts of filtration versus ventilation on influenza transmission in commercial buildings, and we also estimated the cost of doing so. And so in work like this, we essentially found that filtration in the black line was pretty consistently cheaper than bringing in more outdoor air through ventilation in those climates under these sets of assumptions. And then number two is that there was sort of a cost optimal point where installing MERV 13 filters really gave like the most cost benefit trade-off, or the most bang for your buck, where essentially you're able to achieve pretty good risk reductions, around a third lower for influenza in this case. And then as you start to improve filtration beyond that, your cost of filtration, both in running the fan to move air through the filter and also to replace more expensive filters, essentially has diminishing returns. So when you see ASHRAE recommending MERV 13 be installed, this is kind of one of the pieces of information that went into informing decisions like that. And then finally, on this note of quantitative risk reduction, it is useful to know that there are some risk calculators out there available here. We linked to 3 of these that are available out there that have essentially transformed some of these risk calculators and or risk calculation approaches into online calculators. So, if you're interested and you're considering, ways to enhance loss mechanisms in your space and what it might do for COVID-19 transmission, you can use these types of calculators to get a quantitative target of just how much virus-free air or how much greater viral particle loss rates you're going to need to be comfortable in your space. So you have some tools available to you.
All right, great. So now that we've laid a groundwork for how to understand the evaluation of air cleaners in terms of their effectiveness using mass balance tools, as well as why we want to understand that effectiveness from the standpoint of risk reduction, let's dig a little bit more in depth into interpreting the data that we have available to us to make these decisions and how it's acquired. Essentially, what information is available to us to increase this loss rate due to air cleaning that can be introduced into a space. And we'll look at this both in general terms and start to look specifically at different classifications of air cleaners. One of the most important tools that's available to evaluate air cleaners, and this can apply to essentially any type of air cleaner, is with what's called a pull-down test method. A pull-down test happens in a controlled chamber, so this is not a field test that would happen in the environment where the air cleaner is installed, though you can do a pull-down test in that type of environment. But I'm referring to, in this case, a controlled chamber where we inject a challenge concentration of some pollutant. We allow for it to stabilize over some period of time. And then we observe its decay as it's removed from that environment due to the loss mechanisms that are present in that space. The way these tests are done, it's done in a controlled chamber so that you can repeat the test. Do it once with the air cleaner on, hold conditions constant, repeat it with the air cleaner off. That gives you what's called a test condition and a control condition. This test has been used and has been demonstrated to be effective in terms of evaluating the air cleaner for particles, for gases, for microbes. So for all 3 of those classes of pollutants that Brent mentioned in our ideal air cleaner evaluation matrix. So the outcome of this test is, from this dynamic period, we can look at the pull down and evaluate the total loss rate in the chamber. And again, we do that with the air cleaner on and we do that with the air cleaner off. We compare the change in that total loss rate, and the change is due to the addition of the air cleaner. So if we think back to the mass balance that we looked at previously, we might think of it as when the air cleaner is off or not present, there may be 3 mechanisms contributing to this pull down or this decay of our constituent we're testing for. It could be ventilation of the chamber if there's airflow through the chamber. If it's a microbe, it could be an activation of that microbe. If it's present in a particle, it could be deposition. When the air cleaner's on, those 3 mechanisms are still present and should be, the test should be controlled to hold those as constant as possible, but we've added an air cleaner. So if we subtract LAC on from LAC off, if we subtract those 2 loss rates, the difference is the effect of the air cleaner, okay? And that allows us to calculate the clean air delivery rate of the air cleaner if we know the volume of the test chamber. Okay, let's look at an example for probably the type of test that's most common for air cleaner testing via pull down method. And that would be what we've classified as a subtractive portable air cleaner. So this is a mechanical filter, fan and filter system in a portable assembly that's rolled into a test chamber, and we do this pull down test method. So this is actually results from some testing in Brent's lab where they tested a portable air cleaner. And so you see what's happening here on the left is the data, the measurement of concentration in the test chamber, where particles are injected, and then the orange line shows injection and decay with the air cleaner on. Following that test, particles are injected again to about the same level. In this case, the air cleaner's off, and we see the pull down with the air cleaner off. So notice the difference in the shapes of these two curves. With the air cleaner on, we see a much more rapid pull down. We see lower particle concentrations quite quickly with the air cleaner on. Compare that to the shape of the curve of the pull down with the air cleaner off. We see a much more gradual decay. The way we interpret this data is we calculate the loss rate constants. So again, we're calculating this total L during the test with the air cleaner on and air cleaner off. We do that by transforming the data using a natural logarithm. And we plot the data that's log transformed and calculate the slope of the regression that results from plotting the log transformation of that data. So these slopes here that you see in the equations associated with each curve refer to the loss rates that are present during that pull down test. So the outcome of the test is we see this loss rate enhancement in the test chamber, and that's equal to the clean air delivery rate divided by the volume of the test chamber. So a simple rearrangement allows us to calculate the clean air delivery rate. It's the difference of the loss rates with the air cleaner on minus with the air cleaner off times the volume of the test chamber. So we see in the inlay of the figure an example of that here. The outcome of this test was a clean air delivery rate of 258 cubic feet per minute, which is simply the difference of these loss rates times the volume of the test environment, which in this case was around 1,300 cubic feet. Okay, so there's lots of other information available. I'm going to hand it off to Brent, and he's going to talk about some of the different types of data that's out there for other classes of air cleaners.
All right, great. We'll go kind of through a couple different classes of air cleaners. We'll stick with portable air cleaners, whether they're additive or subtractive or both in nature, doesn't really matter at the moment. And stick with the CADR metric because it is widely used and widely understood, including by manufacturers. And so in the top left here, I'm showing a sample of a few hundred air cleaners that I got a few years ago taken directly from the AHAM AC1 like air cleaner test database. So these have been tested in this standardized way, and then in CADR for different particle sizes reported. You're looking at dust, pollen, and smoke. These are just different sizes of particles, essentially. And the interesting thing is they're all actually pretty darn close to each other. And so for many technologies, if you know the CADR for just one type of particle, then you're likely to know the other. But that's at least for the air cleaners in this database. Important to note here is that it's very common to see available products ranging in CADR for any one of these particle sizes, ranging from about 50 CFM or so, maybe a little bit lower in the very, very bottom, the bottom left corner of that graph, up to about 450 or 500 CFM. So it's pretty typical to be able to get an off-the-shelf air cleaner that can provide 200 to 300 to maybe 400 or more CFM in CADR, which we know can contribute to loss rates, right? That's kind of the point. And in the middle, you can see a label or an example of a label that's pretty commonly provided on air cleaning products, especially if they've gone through this AHAM certification. So there you can see the CADR. They don't show you the units. You just kind of have to know that it's in CFM in the bottom there for smoke, dust, and pollen. So you get the CADR for the different types of particle sizes. And then also shown kind of in the middle of that label is how many square feet the room that should be that you want to put it in. right? So it's sort of a suggestion of the size room that the air cleaner is appropriate for. So 450 square feet in this case, with about a 300 CADR, a pretty decent air cleaner on the market. And so where this comes from, even though it doesn't look that clear, is essentially indoor particle concentrations by 80% at steady state. So essentially using a mass balance with a couple of simple assumptions, this recommendation comes from essentially reducing concentrations by 80%. How much extra CADR, extra loss rate per volume would you need? And so you also see that there's sort of this rule of thumb where you can estimate this without using the full mass balance calculation, where you can estimate the CADR needed is about 2/3 of the area of the space you want to use it in. So kind of a mixed units thing that doesn't make sense to engineers, but it makes sense to the general public, I hope. And then interestingly, relating back to the steady state mass balance, this 80% reduction actually yields an equivalent air changes per hour, EACH as we show here, of about 5 per hour. So it's like right in that 4 to 6 per hour range that we mentioned earlier is a fairly common targeted range for COVID risk reduction. It just kind of coincides with this sort of 80% reduction, more or less. So to some extent, you can use these labels to try to infer what kind of impacts an air cleaning product might have on COVID transmission in the space. And then finally, in the bottom left, we just take that same calculation and scale for like different room areas. This is directly from the EPA air cleaner guide to air cleaners in the home for different, like 5 or 6 different room areas from 100 to 600 square feet. What would the minimum CADR and CFM need to be to achieve that 80% reduction? So there's actually a lot of information out there for a lot of portable air cleaners, whether they rely on additive or subtractive means. Next slide. Now moving down the matrix of types of air cleaners for additive, either in-duct or portable air cleaners. Remember, these are air cleaners that add constituents to a space, often reactive to try to engage the mechanism that they're purported to utilize. These are generally tested following a pull down method. That's kind of what we've seen in the industrial literature quite a bit. So the same type of pull down, pollutant injection and decay with and without the air cleaner operating. The same type of method, very similar to portable air cleaners, like Elliott mentioned. One key piece here, though, is that these are often conducted via non-standardized test methods because the industry just hasn't really evolved at this point standardized test approaches like an AHAM CADR test for these types of air cleaners, although there's lots of motion going on to another thing, of course, we mentioned is the potential for byproduct formation. So when you're adding reactive constituents from an electronic air cleaner, whether it's an ionizer or a plasma generator, a hydroxyl generator, or whatever it might be, you do have the potential for some byproduct formation that is conceivable and has been demonstrated just a tiny bit in the literature. You want to know, is that measured and reported? But unfortunately, it's seldom reported. And then also important, as Elliott will go into more detail in just a few minutes, is that the manufacturer provided data from a pull-down test like this on an additive air cleaner are very often not directly in the form of CADR. And so we'll help illuminate that just a little bit. On the right here, you just kind of have a common test setup where, an in-duct air cleaner might be installed in front of a fan to add the constituents to the space and see, what level of constituents are added to the space, and what kind of impact does it have on, say, particle concentrations or microbial viability and so on. Now moving on, slide 39 here. Good, thank you. For in-duct subtractive systems, especially in-duct subtractive systems like filtration and UVGI, we do have some available information to estimate, quantitatively an increasing loss rate. So here depicted on the left, we have this kind of picture of a recirculating HVAC system with a filter. That filter can have a single pass efficiency, this little Greek letter eta, meaning we know how much, to some extent, particles are removed as they pass through that filter. And then for a system, you can also know and measure its flow rate through that. So we can get the product of those two, which is the CADR, divide that by the volume of the space where it's installed, and you can get this sort of extra loss rate that's introduced by an air cleaner. So we can quantitatively estimate the impact on loss rates from something like an in-duct filter and even a UVGI type system. And so the way we can do that is that the ASHRAE standard 52.2 test procedure is an in-duct test procedure that not all, but many HVAC filters are subject to and tested, and you come out with what's called a MERV rating, a minimum efficiency reporting value. And this is just kind of, I know it's hard to see, but it's a table of the minimum efficiency values that come out of that test from 3 different particle size ranges. And so MERV 13, we've mentioned before. If you look across that row, essentially a MERV 13 filter from this lab test has to have an efficiency, a removal efficiency of at least 50% for the smallest particle sizes, 0.3 to 1 microns that are tested in that standard. And then for 1 to 3 micron particles, you've got to have at least 85% efficiency from the test. And then for the biggest particles, 3 to 10 micrometers, you've got to have at least 90% efficiency. So we'll kind of center around MERV 13 since we've explored that. So what do you need to know? You need to know the MERV rating. For example, MERV 13 you've been given, and you need to know the flow rate, in the space. And you may need to hire an HVAC engineer to understand things like the relationship between increasing filter efficiency, causing excess pressure drop. Does that affect the flow rate, and so on and so forth. Or you may need to get more information to even know what your flow rate is in the first place. But the point is, it's quantifiable. And then we can quantify this effective loss rate on viral particle removal, like Elliott suggested on the next slide, with a little bit of estimation approach. And this is something we've done in the literature and others have as well. So you can take kind of a typical resulting removal efficiency curve on the left. So this is the product for like 3 different filters from the 52.2 test. So look at the purple curve there, for example, MERV 14. It shows us that particular filter, like many filters, is better at removing bigger particles than it is smaller particles in this test standard. And then that MERV 14 is better than MERV 6, which is in blue. So we can take those removal efficiency curves. And if you think back to how I introduced us in the first place, where we showed a little bit of literature that had detected SARS-CoV-2 genetic material, RNA, in aerosol samples that were size resolved, right? There was like this distribution across different sizes of particles in the air. Well, you can kind of map these two and estimate in the blue bars there on the right, the estimated filtration efficiency for airborne viral particles. It's imperfect. This is done here in this work for what we assume to be influenza viral distributions, just based on about 7 studies that had measured size-resolved influenza concentrations in different indoor environments. But what we get is this like approximation of viral particle removal efficiency, where MERV 10 is not very good, maybe only 10% removal, so it's not very effective. MERV 7 is better, maybe 40% on average. MERV 13 gets up over 80%, and then kind of diminishing returns from there. And so to show you how you can quantify with some, reasonable accuracy, the impacts on loss rates that this might be able to add to a space, just simply increasing filtration efficiency. Let's do a quick example at the bottom. So for a typical commercial building, it's pretty common to have supply airflow rates ranging anywhere from about 0.3 to 1 cubic feet per minute, CFM, per square foot of floor area. This is kind of a rule of thumb that works out. You can have higher, you can have lower, but that's kind of a reasonable range of many commercial building supply airflow rates. So let's assume that's all 100% recirculation air, just kind of a conservative estimate. Let's assume conservatively an 80% viral removal efficiency from a MERV 13 filter. If you multiply 80% times those two bounds, you get about 0.25 to 0.8 CFM per square foot in deliverable CADR to a space. This is assuming the space is well mixed and so on and so forth. And then if you assume, say, 1,000 square foot space that has 10-foot high ceilings, we get a 10,000 cubic foot volume. Well, then you just multiply that area times that ratio, you get about 250 to 800 CFM of CADR that's achievable. well, hey, that's right in the range of sort of a good to a great to even a maybe non-existent portable air cleaner because it's quite good, right? 250 to 800. That's a lot. That's a lot of viral-free air if we follow this along. Divide that by the volume of the space, 10,000 cubic feet. That works out to about 1.4 to about 4.8 equivalent air changes per hour, achievable by simply increasing the level of filtration in the space. And of course, you can get on towards the higher end. You're looking towards, close to 5 equivalent air changes per hour. You could do more than that. There's certainly commercial systems that move double that amount of air. So you can have some real impacts on increasing loss rates for viral particles just using this type of approach. So again, this is another reason why MERV 13 has been recommended by ASHRAE. And Elliott mentioned this briefly. I do want to show you 2 examples in case you're interested. For in-duct systems, subtractive systems especially, but also additive systems actually. The effective loss rate can also be estimated from an in situ pull down test, meaning it's conducted in the actual space that it's installed. So it's a little tricky to do this, but we've done it here. Actually, in my PhD work, I did some on the right here in a test house for particles of various sizes under different filtration scenarios. And on the left, there's another example of sort of this in situ pull down test. So you can see the line that's pretty straight flat across is just no air cleaner operating. And then all those different curves moving downward show concentrations of particles in time with different types of air cleaners. You can see this sort of pull down efficacy test. We did the same sort of thing and then calculated on the right there effective loss rates. So just look in the middle at 1 to 3 micrometer particles, for example. With the HVAC system on but no filter, we're able to get maybe 1 air change per hour. And then by upgrading to MERV 11, we're able to get like 5 air changes per hour equivalent loss rate. 5 per hour equivalent loss rate for those particle sizes. And so it's possible, but very seldom done to do this sort of in situ efficiency test.
All right, so we've looked at a lot of different types of systems and the typical information that might be available to you to evaluate the extent to which you're increasing the loss rate of the space, for example, by knowing the clean air delivery rate of the air cleaner. The goal there again being to realize a high target effectiveness intervention. Obviously, in reality, the effectiveness of an intervention may not be realized even if you predict a certain value from a mass balance for a whole number of reasons. But it's important to have this idea of sound principles, mass balance based approaches that let us make an estimate of what we expect to happen. And so the final type of information we want to help you make sense of are air cleaners that don't report a clean air delivery rate or haven't been covered already in terms of the information that is out there that lets you report something like the clean air delivery rate. And so Brent's already mentioned this. A typical example of this type of information might be, some constituent PM2.5 or the activity of SARS-CoV-2, 99% removal in an hour. How can we translate this information in a way that allows us to evaluate this device's effectiveness in the target space? So let's look at this in more depth and we'll do a couple of examples. But first, the types of test reports that report information in this way include a lot of different language. So we'll try and briefly present some of the more common terms and define them. Hopefully these next few slides can also serve as a resource that you can refer back to as you're evaluating test reports. A test report should ideally include information on these 5 topics. It may not be present and complete in all 5 topics, but that could then prime you for questions to ask a manufacturer, for example. At a minimum, there needs to be some measurement of the removal due to the air cleaner. Ideally, testing results with the air cleaner on and with the air cleaner off. Each of these 4 bullets I'll talk about in the next slide that refer to different ways that you may see that removal reported. Each of those removal measurements, we should know the time after the start of the test that removal was measured. We should know the volume of the test chamber. We've already brought up volume a few times. We'll see in these examples that volume is quite critical in making the translation from a test chamber to a real environment. To some extent, there should be consistency of certain conditions between the test and control. So things like temperature, humidity, and light should be held constant between the test and control conditions. and the injection of some challenge concentration should be consistent as well. The final point, point 5, we'll talk more about in some of the conclusions of this presentation, but really simple, some very simple questions to try and understand is, what are things like the device settings during the test? Even as simple as, was the test conducted with the air cleaner powered on low, medium, or high if there's 3 settings? And is that representative of how you'll use the air cleaner? For additive air cleaners, you might want to know, what constituents are added, to what levels or concentrations were they added during the test, and at what locations were they measured during the test. For these additive air cleaners, there's been evidence of steep gradients of some of the added constituents, and so it's a good idea to know what was measured, where, and at what levels the test was conducted. So briefly focusing a little bit on that idea of measurements of removal, you might see language used in test reports that fall under these 4 categories. You might see measurements of concentration, which we've talked about already in this talk, some absolute measurement of the constituent we care about. From the standpoint of infectious virus, you might see TCID per volume, tissue culture infectious dose. There are other relative measurements, things like a percent reduction, which is simply some measurement of concentration initially, minus the measurement of that same concentration at a later time, which should be smaller, divided by what was initially present. So if you start with 100, an hour later you have 50, that would give you a 50% reduction. Log reduction is another relative measurement. It's put onto a log scale. So we take those concentration measurements at some later time, divide by the initial concentration present, and take the natural logarithm. The net log reduction starts to get a little more complex. Essentially, this is similar to the log reduction, except we're embedding the control condition into the single metric that's reported. So for the control condition, we take the log reduction I just explained and subtract it from what was realized during the test condition. And that lets you report in one single value the impact of the air cleaner accounting for what happened during the control test.
All right, so let's take some of these terms and walk through an example to try to interpret some air cleaner test data. And so this is sort of a hypothetical generalized example, but you've probably, if you looked in this space at all, you've probably seen information like this. And so let's assume that you've been handed a test report in which E. coli was aerosolized in a test chamber and its viability was measured over time. The test chamber is reported from this independent or third-party test lab as being 500 cubic feet in volume. And so step 1, what you'll do is just collect that performance data. Typically, you'll see reports like this on the left, or maybe figures like this on the right, where essentially you've got the concentration of E. coli. In this case, that's used as a surrogate for other pathogens, recorded at various time points. And so in the table on the left, you've got samples taken, at time 0, 15 minutes later, 30 minutes, 45 minutes, and 60 minutes. So it's an hour-long test. They're both starting at 5,000 colony-forming units, CFU per cubic meter, at the same initial concentration. And in this case, control refers to the baseline conditions. So this is baseline biological inactivation that just occurs in the test chamber. And then test is the intervention. So basically air cleaner on versus air cleaner off is how this is typically done. So in green on the right, I'm just showing those same data, concentration over time and those circle data points. And the green is the control. So you do see this sort of E. coli inactivation or this reduction in viable concentration as the organisms lose viability and or ventilated and or deposit or whatever it may be to the chamber. And then in orange, you see this steeper reduction from this kind of pull down test from the intervention, the air cleaner on period. And then often what's reported is what we showed earlier is, hey, at 1 hour, you've got 99% reduction in E. coli. That's an effectiveness of 99% in this test chamber. That's fantastic, right? You've gone from 2,000 CFU per cubic meter to 100. Big impacts in this particular case, right? And that's what you're basically left with to try to evaluate. But what we want to do is interpret this and translate it to other spaces than just this test environment. So on the next slide, what we'll do is take that performance data that was collected, I'm just leaving the concentration there on the left. We're going to take that data and we're going to fit it to a first order exponential decay model. And so this exponential decay model is just shown visually down in the bottom right. It's just sort of a normalized concentration where at time 1, or time 0 at the very beginning, you're at 100% of the max concentration, and then you decay at some rate. It's a function of the net loss rate in the chamber, or the total loss rate in the chamber. And so this is just this typical first order exponential decay model that can be used to describe decay due to anything, biological inactivation and other mechanisms as well, as long as they operate at that sort of in this sort of first order nature. And so we transform these data points in the table on the right at each time point, where we essentially take the natural log of the E. coli viable concentration at each time divided by the initial concentration at T0, and we just place those, and we have the sort of string of sort of transformed values. What we then do is follow this exponential decay model. We plot the natural log of the concentration each time T divided by the initial concentration versus time. And what that'll do is give us the resultant loss rate for each scenario. So in slide 3 here, we visually plot these data. So the natural log of the concentration each time divided by the initial concentration on the y-axis versus time. And this, we essentially fit a linear regression through those data points. And the slope of that line, hopefully it is a line because it fits a relatively reasonably, fits this log linear exponential decay line. So hopefully you've got a straight line with reasonable regression statistics like R squared of 0.95 or higher or something like that. And then the slope of those lines is the effective loss rate from each one of these conditions. And so in green, we've got 0.0145 per minute is the loss rate at baseline. And in orange, you've got 0.06 per minute loss rate. So indeed, the test intervention has a higher loss rate in this scenario. And then, as Elliott described earlier, we can determine the effective CADR or the equivalent CADR from those loss rates to put it on the same kind of comparison plane that we can compare to other technologies that we know more about. And we simply just subtract the loss rate estimate with the air cleaner on minus the loss rate estimate of the air cleaner off times the chamber volume, so 500 cubic feet, and we get the CADR. In this case, we have our numbers switched around. We would get a negative number here, which is a funny number. So there's this little typo. Those two numbers should be swapped. That's our bad. But regardless, you'd end up with this number of about a 22 CFM CADR, right? And so now we've translated from 99% efficacy of reducing E. coli, viable E. coli in a 500 cubic feet test chamber to an equivalent CADR of about 22 CFM. And so on the next slide, we can then try to scale that to a space that we might want to operate it in to understand how it compares on this basis of loss rates. So let's scale the results to the targeted space installation. Let's use the volume of the space that we want to install the device in. And we're going to assume we're designing this air cleaner for use in a conference room. We're going to assume that's 15 feet by 25 feet, so 375 square feet area, and say 10-foot ceilings for simplicity, so a volume of 3,750 cubic feet. And so we can calculate, if we can assume that the air cleaner's performance would be reasonably similar to how it was in the test chamber, which is another question that we can get into in a moment. But if we can assume that, we can calculate the additional loss rate due to the air cleaner by multiplying the CADR, 22.4 cubic feet per minute, times 60 to get it on an hour basis, divide by the volume, 3,750 cubic feet, and we get an additional 0.35 air changes per hour. So remember, our typical target for an added loss rate that we've sort of meandered through here in this presentation is, maybe on the order of 5 equivalent air changes per hour, 4 to 6, those kinds of numbers. In this case, 0.35 would be about an order of magnitude lower than that recommended level. So the air cleaner would be undersized for the space. So you would want to reconsider sort of the options that you have available.
Okay, so that example illustrates a really important concept, and that is that the CADR determined from an air cleaner test scales with the test chamber volume. We're showing the equation here where you see that we multiply the difference in loss rates times the volume of the test chamber. So CADR is proportional to the volume of the test chamber. And this is really important because for a whole range of very valid reasons, different size test chambers might be used to evaluate air cleaners, everything from very small chambers that might be, on the order of a cubic meter, to large chambers that might be approaching the size of a small office. Testing, obviously, as we've discussed, can happen in real field environments, but a wide range of chamber test volumes are used in practice, and especially in non-standardized test approaches. So it's really essential that we understand how to link the results from a test done in a chamber to what we think might happen in the real world. And as Brent mentioned, the clean air delivery rate is this sort of tool that allows us to make comparisons on a similar plane and also to make that link between a test environment and what we think will happen in a real environment. So let's look at an example. One of the graphical tools that we've developed to try and help make sense of this and to quickly interpret this type of data of the form, 99% removal in 30 minutes or so, is this chart that essentially summarizes these test results in terms of the loss rate enhancement realized in the test chamber, and then allows you to quickly scale it to what would happen in terms of this clean air delivery rate that would come out of that test. So let's use this graphical tool that's shown here on the left in a quick example, and I think this will make sense. What's plotted here on the horizontal axis is the time to achieve a certain fractional removal or percent removal. The different colored lines show a different percent removal achieved across the times plotted. So let's consider the result 99.99% removal in 30 minutes. To use this tool, we look on the horizontal axis at 30 minutes, go up to the yellow line, which we see corresponds with 99.99% removal, and we track over on the vertical axis. And what this tells us is the clean air delivery rate per test chamber volume, essentially the loss rate enhancement in that test. And the units of this tool are in CFM per cubic foot, which we'll see why that's presented in that way in a moment. So for the moment, let's take that the value from this graph is 0.3 CFM per cubic foot. This is on log scale, so we're at 0.3. So our result is 0.3 CFM per cubic foot. If we want to understand what the clean air delivery rate from that test would be, we'd need to know the chamber volume. So if the test was conducted in a chamber with volume 10 cubic feet, we'd simply multiply 10 cubic feet by 0.3 CFM per cubic foot. If those were the conditions, our clean air delivery rate would be 3 CFM. This scales according to the volume of the chamber. If it were a 100 cubic foot chamber, it'd be 30 CFM, so on and so forth. 1,000 cubic feet, 300 CFM. So the important takeaway here is that a wide range of CADRs, ranging from a very low CADR of 3 CFM to sort of getting into the average value that Brent reported from a wide range of assessment of portable air cleaners, 300 CFM, can all claim 99.99% removal in 30 minutes, depending on the test chamber volume. So again, really important to know that test chamber volume. Let's look at this in a slightly different way. Let's imagine we know the clean air delivery rate of an air cleaner, and we were to put it in a 500 cubic foot test chamber. Let's ask ourselves, what percent removal would be achieved in that 500 cubic foot test chamber in 30 minutes if a 250 CFM CADR air cleaner was present? So we can take the same idea. Let's imagine a pull down test is conducted and this air cleaner is reducing the concentration of some constituent we care about. In this example, we've just normalized it to a value of 1 because we care about the sort of dynamics or the rate at which this pull down is happening. So in a 500 cubic foot test chamber, a 250 CFM CADR air cleaner in 30 minutes will realize 99.99997% removal in 30 minutes, or more than 6 log removal if it's on a log basis. So the takeaway here is that the idea that an air cleaner is realizing over 99% reduction on timescales indicated of tens of minutes to hours, that should be the case. And in fact, an air cleaner with high CADR should be realizing 99.999 on that order of magnitude, much more than 99% reduction. Okay, so these calculations I mentioned early on require that you make some, you have some understanding of mass balances and logs and natural logarithms. And so we understand that some of these calculations, you may not want to work through by hand yourself, for example. And so we've developed some tools to help through this, sort of responding to um, the CDC's guidance, for example. In their FAQ document on ventilation, they state that many new air disinfection devices are marketed for their ability to inactivate SARS-CoV-2. How can I tell if they work as advertised? And the CDC's response is that consumers are encouraged to exercise caution and to do their homework. So we hope that this presentation and the tools that we are putting out there help you in quote unquote doing your homework. So one of the tools that we developed is the graphical image that I showed previously. We also developed a spreadsheet tool where you can directly input data through a variety of scenarios to make calculations that convert data of this type, this percent removal data, to a clean air delivery rate. And we call this tool ACIT, the Air Cleaner Efficacy Investigation Tool, developed by Brent and I and a few other colleagues. You can access this tool on pdx.edu on the link provided here. Right now, I'll take a moment to just show you the spreadsheet and walk you through one very brief example to show how the spreadsheet works. So bear with me while I cancel out of the presentation and bring up that on the shared screen.
And while we wait, Brent, Elliott, I'll ask you try to wrap it up in the next 10 minutes or so, so we have time for questions.
Sure, of course.
Thank you.
So I'll keep this this example brief then, and just reiterate that this spreadsheet is publicly available. You can click on the link provided and you can download a copy of the spreadsheet. There's an overview slide that explains the different cases that essentially allow you to input data in a slightly different form. So I'm showing an example here that we can briefly walk through that we'll do with ACIT that's not dissimilar from the previous example that Brent worked through in the slides. Imagine there's a SARS-CoV-2 inactivation test that was conducted in a 1,000 cubic foot chamber, and out of the test report came log reduction as a function of time for both control and test conditions. We want to install this air cleaner in a space that, as in the previous example, is 3,750 cubic feet. So this is all the information that we need to use this spreadsheet tool. Over here on the right, I'm showing the Google Sheet that is the spreadsheet tool that you can use to help make these calculations. In all of these spreadsheets, the inputs are shown in orange and the outputs are shown in green. So your task in using this tool is to collect data so that you can input everywhere where you see is orange. Okay, so for log reduction data, we mentioned in the slides previously that there is log reduction and net log reduction. If the data that you have is reported in net log reduction, you change this cell from 0 to 1 and follow some of the notes that guide you through that. So there's additional guidance here if you scroll over into the notes. For this example, we have data reported separately for the control condition that's already input here from the test condition, which is already input here. So you would take this table of data, translate it over into the spreadsheet. The spreadsheet then does the natural logarithm transformations that Brent discussed for you, making those calculations and putting this on a natural logarithm basis. You see a plot of the curves that Brent mentioned. The regressions are done separately in the spreadsheet for you so that you can calculate those loss coefficients that are needed. Here in the spreadsheet, we input the chamber volume. In this case, the test chamber was 1,000 cubic feet, so we put in 1,000 cubic feet here. So we scroll down and we see that in green, these calculations are done for you. The spreadsheet calculates for you both the loss rate enhancement and the clean air delivery rate realized from this air cleaner test. Scroll down to the next section and the spreadsheet helps you do the scaling to the indoor setting that you want to install the device in. So in this case, we're looking to evaluate air cleaners for a 375 square foot space with 10-foot ceilings. The spreadsheet does the calcs to show that you would realize 6 per hour of additional equivalent air changes per hour by introducing this air cleaner into your space. Okay, so this spreadsheet helps you make that connection between a test environment to a real environment that you are concerned about and evaluating air cleaners for. Okay, so with that, I'll go back to our PowerPoint. Bear with me and hand it back over to Brent.
All right, for the sake of time, we've got a slew of sort of other considerations, some of which I bet will come up in the Q&A. The first is when you're thinking about a portable air cleaner, maybe you've seen this visualization in the New York Times from February of this year. You know, certainly for a portable air cleaner, performance can be impacted by its placement, its location. And so this shows results of some computational fluid dynamics simulations. There's sort of a lot of weeds to get into here. And so short of detailed investigations of a particular space, some of the high level generalizations that you could sort of glean from this are, you know, it would be great if you could put a portable air cleaner near a known infected individual, but you almost never actually know who that is. So that's, you know, near impossible. If you're doing ventilation, say through open windows or through a fan in the window in a school, where you don't have a lot of capacity for HVAC ventilation, well, then you don't want the air cleaner to be sort of right in the flow path of that clean air, right? You don't want to kind of you want to make sure your layers are additive in that sense. And really, it's hard to generalize, you know, frankly, in many environments, place it wherever you can practically put it, because a portable air cleaner and its operation might be impacted by other factors like, on the next slide, noise, right? So portable air cleaners have been shown in a few studies to be used less frequently over time, and some of this have noted or speculated that it's because of noise. EPA has some levels of interference and annoyance above which a certain decibel level of 45 decibels, for example, indoor noise becomes an annoyance. Many portable air cleaners that have been tested for noise do actually exceed this threshold, but quantified noise is not routinely used as a standardized performance metric in the US here, at least, and it's not routinely available in product packaging. And just on the next slide, there is sort of this unfortunate situation where many portable air cleaners are often loudest at their most effective setting. So this is just some research from about 5 years ago, measuring noise production for a couple different air cleaners at different fan speeds and therefore different CADRs. And moving more air at a higher, you know, maximum fan speed was also when the units were loudest. And so this practically just might mean that, say you've got a targeted CADR you want to provide in a space. If your air cleaner is too loud, you might have to get two of them and operate them at, you know, lower noise levels or something like that. Another consideration to just be thinking about is ozone emissions or other sort of constituent emissions. So we do know that some electronic air cleaners emit ozone. In 2014, there's a really great report from Glenn Morrison and colleagues on in-duct air cleaning devices and ozone emissions from those. And essentially, there's a wide range of emission rates. You know, some UV systems, some sort of reactive oxidant generators didn't really emit much ozone. That's, you know, broadly a good thing. Whereas others emitted a large amount, and it sort of varied. You know, there was a case even when a UV product emitted more ozone than a dedicated ozone generator. So you want to just make sure that this is quantified, for example, by following UL 2998, which essentially just allows no more than about 5 parts per billion of ozone in a standard test chamber to result from operation of an air cleaner. On the next slide, we mentioned the potential for byproduct formation before. You know, again, the idea here is that for any kind of additive or reactive type of air cleaner that adds reactive constituents to the space, you want to know, you know, what might that be doing to the constituents, for example, gas phase compounds like VOCs in the space. So what that will do is add, you know, these additive reactive sort of constituents, you know, to the space and essentially react with some kind of challenge mix. So whatever VOCs and so on are there in the first place. And what you want to know is what's formed from that. You know, is anything formed, or do you have a net reduction, or is there a change in the sort of balance or mix of products that are generated? So there's one slew of VOCs that are present normally from things like building materials and occupants and so on. Does it convert into something else? Or are there other gas phase products or particle products that you need to know about. And we just show an example here of some recent field tests that we did with a ionization device installed in an air handler in a building, and just measured VOC concentrations upstream and downstream, and we saw some increases in some constituents and decreases in others. So the point here is that we'd like to know more about this space, and it's sort of an emerging but small body of research on this. Elliott will touch on two more of those, and then we'll wrap up.
Yeah, thanks. So looking across the literature, like Brent said, there's not a whole lot out there right now on some of these emergent or electronic additive air cleaners, but there are studies that have come out in the past year that have informed our understanding of some of these devices. A recent study came out this year in Building an Environment, tested 12 additive air cleaners looking across 3 general types of mechanisms: PCO systems, photocatalytic oxidation, non-thermal plasma, and ozonation that they tested in a controlled recirculating duct in a lab shown in the upper right. And I'm highlighting one result from this study just for PCO systems, where they plotted on the horizontal axis the acetone removal efficiency. So this was one of the VOCs they tested for removal across these PCO systems. They also looked at byproduct formation, and what they showed was that acetone removal efficiency is in the order of 0 to 10% for these systems. And that as it increased from 0 to 10%, in general, the byproduct generation rate increased as well. And they were measuring formaldehyde and acetaldehyde. Another recent study looking at byproduct formation from a different type of additive air cleaner. This study is a preprint, so it has not yet undergone peer review, but they placed an oxygen generating air cleaner into an office. This air cleaner generated hydroxyl radical and hydrogen peroxide. This is not a pull down test. This is an example of a field test where they put the device in the office for some amount of time with it turned off, turned it on for about an hour and a half, and then turned it off again. And so the high level takeaways here are that these two plots on the right, the shaded area in yellow is when the air cleaner was turned on. And in the top plot, what the researchers found was enhancement in certain low molecular weight oxygenated VOCs. So we see on this normalized signal increases in certain VOCs, not dissimilar to what Brent was just discussing. In the bottom, what we see is various metrics of particulate matter. And let's just focus on the red plot, which is the number concentration of particles. And so we see when the device is turned on, a substantial enhancement in small particles, the researchers suggest due to particle nucleation and condensation mechanisms that bring us from around a background of 500 number per centimeter cubed up to over 4,000 number per centimeter cubed at the end of the test. So the result is that it appears that there is potential for byproduct formation from this particular device. Like Brent said, there's a lot more we want to know about these kinds of devices, and standardizing the way in which we do these tests so that there can be some comparable metrics in terms of byproduct formation results from different devices. Okay, so we're wrap up and provide some closing thoughts briefly. I won't go through this list in full detail. Really, I think a list like this is something of a resource that you can refer back to. So in this slide, we've compiled some of our thoughts from putting together this talk, as well as our research over the past few years and in general, of what questions you might ask as you're interpreting a laboratory test report. So hopefully, as you work through these bullet points, the materials that we present in this presentation, and some of the tools that we've provided help you understand what's being reported in a laboratory test report, or how you might interpret a laboratory test report to get to something like a clean air delivery rate. Is one, I think, really important and key conclusion from our presentation here, is that a metric like CADR is something that allows you to conduct this scaling from a test environment to a real environment that we think is so important in evaluating the impact of an air cleaner.
And just to wrap up, the same sort of thing here for the details that we would recommend that you seek for any field test reports that try to demonstrate or attempt to demonstrate air cleaning technology efficacy. So there are standard sort of field test method There's standards and guides that are available that we link to, making sure to do things like measuring indoor and outdoor pollutant concentrations at the same time, depending on what they're measuring. You want to make sure that, appropriately and sufficiently sensitive instruments were used. And, for some technologies, especially additive, technologies, you want to make sure that sort of how much of those additive compounds or whatever it might be are present in the space, and were any byproduct tests performed, and so on and so forth. And as we move forward on the next slide, charting a kind of path forward, we're left thinking of a number of research needs. There's a number of fundamental studies that should be conducted to elucidate underlying mechanisms of action of a number of air cleaning technologies for which we don't know a whole lot about. And manufacturers can explain as clearly as possible those mechanisms and communicate that to relevant stakeholders. We need more studies in both well-controlled environments, which have their own limitations, but they help us understand mechanisms, as well as less well-controlled environments like real field studies to evaluate real-world efficacy and impacts. And as we move forward, we'd like to see improvements in test standards across this sort of ideal matrix that I had put forth of like, let us know what's the particle, chemical, and or microbiological efficacy and or byproduct formation. And where we're at now is that for efficacy or effectiveness, standards and methods do exist, but they're, incomplete. And there's just not a lot right now on byproduct formation to the extent that that's important for some technologies. And so with that, we'll wrap up. I know we had a lot of information, but we want to acknowledge, of course, first and foremost, our own research groups at our two institutions and those who have come through those throughout the years. Also, this information and this presentation wouldn't be possible without a large number of collaborators and mentors and colleagues, both past and present over the years. And so a lot of what we've put together today is sort of a culmination of many years of knowledge from ourselves and others. And of course, thank you again to US EPA, Laura and Vito, especially for bringing us on. And with that, I think we can open it up to the Q&A portion.
Thank you so very much, Brent and Elliott. You had a lot of different things to explain and at different levels of technical skill level here. And so we tried to summarize a number of questions in the remaining minutes here. I will try to address at least some of them. And they're asked in general, not specifically to either of you. Whoever wants to take it, please go ahead. And so I'll start from the bottom line in one sense. So we have some comments and questions saying, well, this is interesting, but it's also complicated. Is there an easier way for me to know if something is safe and effective? And perhaps one thought is you have taken apart and tested a number of products. For example, how good is price as a proxy for effectiveness and safety of these air cleaners in your experience?
Yeah, that's a good question. I'm recalling a plot of I've seen some comparisons on sort of a portable basis in particular, but it's not a perfect indicator. I haven't seen a really clear, coherent analysis. There are some pretty high-end devices that have been shown to not perform very well, right? And there's some low-end devices that have been shown to perform pretty well, at least on some performance metrics like CADR for certain particle sizes. So the box fan and filter, the very idea that exists as a not unreasonable way to increase loss rates for particles lets you know that it ain't linear, is kind of what I think. In-duct devices, I think some of the I think you get a bit more into maybe diminishing returns like we talked about. So in some cases, you could really spend a lot of money on HEPA filtration when MERV 13 or 14 might get you 90+% of the way there. So I think it's an imperfect relationship at this point.
Yeah, just to add to that, I agree with everything Brent said about price, and to respond to the idea of the complexity that was brought up. Hopefully the presentation and some of the tools help address situations that might be complex, but I think it's a fair point And I think, an ideal response would be that if there are standard test methods, it need not be complex. I mean, one of the takeaways of our presentation is that if you know the clean air delivery rate of the air cleaner, it doesn't have to be overly complicated. Go calculate the volume of the environment you want to install that air cleaner in, and it's not going to be 100% perfect in terms of design, but it gives you an idea of what is the enhancement of the loss rate or the EACH you're adding to the space. So for some air cleaners, that clean air delivery rate will be presented front and center, and there are rules of thumb or very simple calculations you can do to sort of distill a lot of this complexity down into one calculation that I think anyone can do. Now, in the case where the data is presented in a different form, unfortunately, yeah, at this point there might need to be some quote unquote homework that needs to be done, and hopefully this presentation and some tools can provide a resource to help with that.
Thank you. We had a number of questions and even more comments about air mixing in the room, and so perhaps you can say something about why air mixing is important. There were even a number of fans in your graphics, and perhaps thinking in terms of approach also, would it make sense to use a ceiling fan or a portable fan in the same room as an air cleaner routinely?
Yeah, there was a recent study that just came out looking at the impact of mixing via ceiling fans on exposure concentrations to proxies of, what were intended to be proxies of virus exposure. And I think the essential takeaway from that study is that, increased mixing allows you to dilute into the full volume of the space, reduce that concentration, because concentration is the amount of whatever constituent you care about per unit volume. So if you're doing a good job of mixing it through the full volume, you make that denominator bigger, reduce the exposure concentration. There are scenarios, and the CDC goes through some of them in the document that was referenced earlier in the slides about scenarios where you need directional airflows, where mixing may not be appropriate. It can get very complex very quickly. Getting back to the previous comment about it being so complex, I think Brent mentioned, it's sort of that baseline. Don't let the, sort of paraphrasing Brent, don't let the perfect be the enemy of the good. If you need to put an air cleaner in the space, for example, do that. And so mixing might be, another example where it can become complex very quickly. But, if there's not a need for directional airflows, there are some studies out there that, indicate that ceiling fans and mixing can help with dilution a little bit.
Thank you. Also in the category of hoped for heuristics to choose again, can you say something about, is it better, let's say, to pick air cleaner that use a combination of multiple technologies? Would they be more effective in general?
It's a good question, and I know a lot of manufacturers have, I think, spent a lot of time, kind of going down that route. At the risk of reiterating ourselves too much, that's sort of the beauty of some of this way of standardized testing, or using an equivalent, kind of clean air delivery rate test, because it's largely agnostic to how you do it. If the air cleaner is a magic, generator of something that is we've never even dreamed of, as long as it can reduce viable virus or reduce particles or reduce gases or whatever in this same sort of test framework, then you can sort of you can take that information and move forward. So yeah, I think it's hard to say. I've seen products that put technologies in the wrong order. Hey, this generates ozone and this removes ozone, but we put it in the wrong order. I've seen that before. It's hard to say a blanket statement of more types of technologies, but certainly you can see products with 5, 6, 7 technologies kind of combined together, often with proprietary type names, so you're not really even sure exactly what it is. Our sort of overarching thought is, well, test it in a chamber, using relatively standardized methods, and those test standards need to evolve. And if you use non-standardized approaches, analyze it in a standardized way.
All right. Another interesting angle is to really look at, I mean, there's a stated effectiveness, and then how do people know if something is working? And do you have any comments perhaps on the use of air quality monitors to assess how this or other mitigation forms may be working?
Yeah, that's a really good question, and I think it's a little bit challenging, specifically SARS-CoV-2. I mean, we can measure particles with low-cost monitors, and one thing you might do is the idea of the effectiveness metric that was presented in our slides can be calculated empirically. It can be calculated from measurements made in the space with and without the air cleaner operating, so you don't need to fully go through the process of a mass balance. Um, the challenge is that it generally is not routinely available to individuals to measure what we care about, which is the virus in particles. And we're talking about very sensitive methods and expensive methods needed to directly measure what we care about. And particles themselves have lots of different sources. You may not be measuring a proxy for viral particles if you take a low cost monitor and measure particles. But with that being said, I mean, I think it's still a useful exercise to evaluate an intervention aiming to reduce particles in a space with empirical methods to make measurements of particles in your space with and without the air cleaner operating to tell you, I expected 5 ACH of equivalent cleaning. And with that, I should see, X% reduction in particles. And so if you do see that, I think that's a sign that your intervention is sort of working close to as designed and should be, affecting those particles that are containing potentially virus as well, even though you won't probably be able to directly measure virus in particles as a sort of member of the public if you're not a researcher with those capabilities.
So following on that, I feel like 2020 was kind of the year that informed citizens learned to use things like CO2 monitors, in their spaces, and even conduct, some pretty straightforward air change rate testing, right? Like get people in a room or inject CO2 from dry ice or from a container or whatever, and measure the decay. Maybe 2021 will be the year of like the low cost CADR test, because you really could get a reasonable signal, burn some incense, elevate particles in some fashion, use a low cost particle sensor, measure the decay with and without the product that you're questioning, operating, hold everything else constant as best you can, and you'll get an approximation of an effective loss rate enhancement that could be useful to you.
Thank you. I didn't leave you enough time really to elaborate on the placement of air cleaners, but an interesting set of questions is about protecting particularly sensitive targets. So instead of so the placement, we know it's more effective. You said in the slide to put it near the source, but what about protecting vulnerable people by putting in the air cleaner near them, even if may or may not be sized for the size of the room? Is it effective? Is it useful as a protective? And so it's still sort of the flip of the mixing consideration here.
Right. I saw this a lot in sort of, dentist office early on or something like that. People who came, and other essential workers who returned to work pretty early and said, I'm carrying a portable HEPA filter or whatever, with me, and I'm going to put it at my desk. From my perspective, the good thing is that if there's reasonable filtration, which most of those devices, especially if they rely on particle filtration, will have, MERV 16 or higher HEPA, the air coming out of that is essentially virus free. It's just a matter of like how much, and so it certainly can be used as a sort of personal bubble protection mechanism in my thinking.
And we have time for just one more question. Do you have any comments on wall-mounted filtration units versus other portable ones?
Yeah, that's a good question. I haven't seen a lot of products in this space. Elliott, have you?
No, I haven't either. I mean, I think functionally it should work if it's an effective air cleaner with a high clean air delivery rate. I mean, you get into some of the same questions about placement that starts to get really complex with the geometry of the space and, airflows in the space and how it's interacting. But, from a personal standpoint, I would love to see more innovation in this area. I mean, you hear a lot of feedback in terms of like, the air cleaner, it's too big, it's in the way, so on and so forth. It would be great to see, good air cleaners that are tested according to standards, that have high clean air delivery rates, that can be integrated into homes in, clever ways that maybe address noise issues and placement issues, so on and so forth. I mean, I have little kids and, I worry about them pulling the plug of the air cleaner and stuff like that. So I think there's a lot of potential for innovation, and certainly wall mounted or other installations are one way that that might be realized.
Okay. Unfortunately, we need to end. So thank you very much, Brent, Elliott, for giving so many resources and information to our audience. Thank you to all those who have participated in our webinar. Remember that a recording will be available and posted on our website, so you can share it with others who couldn't make it today. And thank you again. And this concludes our webinar.
Thank you for the chance.
Thank you so much.